So, we're going to give our lecture on falling objects. You ready? I'm waiting to see if anyone's actually going to start writing that down. No.
Make
stuff fall down at the end. No, that's not my lecture. Okay, here we go. I want you to understand how Galileo figured out gravity. Before Galileo, gravity, everyone knew that gravity, or they knew something was happening, why things were falling down. Maybe they didn't know why it was causing it, but they understood when something dropped, it fell down, and they also knew that it went faster. Okay, so, you know, they could easily drop a pebble from their hand here, or drop the pebble from a high structure, and it would hurt a lot more. So that basically they could figure out that something was speeding up. And people are starting to try to understand it better, but Galileo is going to be the one that best understands it and works everything out. What he does, think about it, Galileo didn't have meter sticks and stopwatches, but Galileo could have set intervals of time. All right, so what he would do is he would have, and to be honest, I might be making this up. I thought it was something like a metronome or something like that to record time, just to have set times, but I could be wrong with that. Let's just pretend I know what I'm talking about. All right, anyways, what he would do is this. If he just dropped stuff, it would be going too fast. So to measure distance when you're dropping stuff isn't really going to work. But what he could do is have a series of ramps at different angles to slow things down. So what he did first was he would have a ramp and the ball would roll down for a set velocity, or for, let's say from here, he'd have the ball roll down and he could figure out how long it takes to go after 1 second or so. Alright, so 1/1000, boom, he'd get a set distance. Alright, and obviously he did it multiple times to make sure his numbers looked good, but 1/1000, whatever that was. Then you go for 2 seconds, 1/1000, 2/1000. Alright, and you can see how long that distance traveled. Okay, and so on and so forth. He could change the angles and the ratios of the distances would stay the same, but obviously what he could do later is do the math and figure out what these numbers were. Okay, what the actual numbers were, but if he goes slow with a low angle, it would be easier to break down at first. But this is what he found out first. After 1 second, whatever that distance was, he wasn't really concerned whatever it was. It wasn't like it was a meter, because obviously if you change the ramp height, that distance would be different. But whatever that first distance was for after 1 second, 1/1000, okay, he would just say that's going to be a measurement of 1. Then he'd run it for 2 seconds. Alright, 1/1000, 2/1000. So after 2 seconds, after 1 second, he got a certain distance here. And what he found out was this. Whatever the distance was from 0 to 1 seconds, from 1 to 2 seconds, this distance in between that time was 3 times longer. Okay? So that's supposed to be an arrow, but it's not oriented. So from here to here would be from 1 second to 2 seconds, however far it traveled during that time, was 3 times the length of what it was after 1 second. Now again, I'm not saying that after 1 second it goes a meter. I'm just saying that after 1 second, whatever the distance is, from 1 to 2 seconds it was going to go 3 times that length. Okay? From 2 to 3 seconds, when he measured the distance between the 2 and 3 seconds, how far it traveled then, it was 5 times longer than this distance here. You want to guess from 3 to 4 seconds how long it went? 7. So from 3 to 4 seconds, whatever the distance was between that time, between the time of 3 seconds and the time of 4 seconds, this would be 7 times longer than however traveled after 1 second. Okay? Now this isn't an equation you're going to use, but I want you to see how Galileo had to get the science behind it, how Galileo had to understand this. So that's how he would break everything down. Alright, now, then you look at your total distance traveled. So again, after 1 second, whatever that was, We just say it's 1. Okay, whatever that 1 is. After 2 seconds, what's the total distance going to be? 1 plus 3, 4, right? So after 2 seconds, the total distance would be 4 times longer than what it was after 1 second. Alright? What about after 3 seconds?
6 times.
Well, we have 4 plus 5.
Oh, 9.
So 9, yeah. So the total distance after 3 seconds, this total distance here was 9 times longer than what it was after 1 second. Okay, you want to guess what the next one was going to be? We have 1, then we have 4, then we have 9, 16. Square numbers. So, tie that all in together, okay? And again, this is not going to be how you're going to be doing your problems. But I want you to understand what Galileo had to go through to get these numbers. Alright? So this is the idea. After, or if we talk about in between the time intervals, okay? From 0 to 1 second, from 1 to 2 seconds, from 2 to 3, from 3 to 4, the distances will match a sequence of odd numbers. And the total distance traveled from 0 to 1, from 0 to 2, from 0 to 3, that will follow a square of the time. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on and so forth. Okay? Alright. Alright. You know what, I'm going to skip that. Oh! Let's go back here. Oh, Lordy. Hit pause. We're good?
I think it restarted, but okay.
Okay. So what Galileo figured out was that velocity is going to be some kind of constant times the time it takes to fall. Okay, and that's basic, and we're going to figure out what that constant is in a second. He understood that the distances in between follow odd numbers. Okay? The ramps could change, but whatever it was after 1 second, it would be 3 times longer between 1 and 2 seconds, and so on and so forth. Alright? The total distance traveled is related to the square of the time. Alright? But the good thing is this. We are going to still use the same equations we've been using already. We're going to use the big 3 still. We have the big 3 for a while. So you don't have to learn any new equations. We're still using the big 3. Really, the only thing that gravity is acceleration. Alright, I'm going to show that in the next slide. You want me to pause while you write? You don't have to write all this down. Okay, I'm going to move on then. Okay, good.
Thanks.
You're welcome. Okay. What I want you to understand is that gravity is really just acceleration. That's it. Now, I say it's not a force, and yes, there is a force due to gravity. There's a force due to the acceleration of gravity, but gravity alone is no different than any other acceleration you are doing already on your worksheets. Okay? We just treat it as an acceleration. So, acceleration, not a force. The acceleration of gravity will always, always, always be negative 9.8 meters per second squared. Always. Alright? We'll still write it as A, but we can use a little g for gravity. So if you see little g, you know what I'm talking about. It's also my rap name. Okay.
What?
2 objects will fall regardless of the mass. Should we know that already? Did you learn like in 4th or 5th grade that Galileo was on the Leaning Tower of Pisa and dropped a... No? So it doesn't matter what the mass is. If I drop a pebble and a large rock, the 2 objects are going to hit the ground at the same exact time. You should know that by now. Just nod your head yes, and hopefully you'll remember you do know that. But it's to the point where anytime you drop any object, no matter what the mass is, they will hit the ground at the same exact time. if you drop a feather and a hammer here on Earth, is a feather gonna hit the ground at the same time as the hammer? No. Okay. But that doesn't have to do with mass. That has to do with air resistance. Okay, so understand that these have the same mass. They still have the same mass. The reason that the crumpled up paper hits the ground faster than the non-crumpled up is not because of mass. It's because of air resistance. Okay? The feather hits the ground faster than the hammer here on Earth because of air resistance. It has nothing to do with mass alone. Alright? Galileo mentioned this, and he talked about a feather and a hammer. In fact, what he did was, he talked about it so much that when the astronauts on Apollo 11 went off and landed on the moon for the first time, they actually took a feather and a hammer, and they said, let's see if Galileo was right. And they dropped the feather and the hammer at the same time. Now, that had nothing to do with the gravity's less on the moon, because obviously it still affects each object the same. So they dropped the feather and the hammer, and what do you think happened? They hit the ground at the same time, because there's no air resistance on the moon. When they drop the feather and the hammer, they both hit the ground at the same exact time. Okay? 1 second. Let me finish my thought here. So please understand, regardless of mass, two objects will always hit the ground at the same exact time. Now, in this class, because we're not an engineering class, because we're not going to deal with air resistance that much, we're going to throw air resistance out the window for now. Okay? We're not going to worry about air resistance. If we deal with a problem, it's going to be a baseball, a cannonball, a bullet, whatever. It's going to be something that doesn't have air resistance. And yes, air resistance can affect it, like the feather, okay? But we're learning physics right now. We don't want to deal with air resistance, okay? AP Physics, yeah, they deal with air resistance a little bit. If you want to be an engineer, yeah, you got to deal with air resistance. But realize every problem we do, there will be no air resistance, okay? Again, that's not really putting us in a fantasy land. We're just not going to deal with certain things that fly through the air that are being slowed down by all these other extra things. All right, let's pause it there.
How do you pause it this time?
Hit the button again, yes. The nice thing about falling objects is that really there's going to be, you have so much more given information every time now. So every time we drop an object, we know right away, you don't even have to read the question. As soon as you see it's question number 1, you can write A is 9.8 or negative 9.8. Does that make sense? I mean, right away, and the cool thing about falling objects and gravity is that there's going to be immediate numbers that you can right away put down. Okay, we're going to talk about, and in fact, we're going to go outside for a lab later on where we throw a ball straight up in the air and let it come straight down. And the only thing you need is a stopwatch. And if you have a stopwatch, you know how long it's in the air. You have so many given numbers and given information that you can figure out how fast you threw the ball and exactly what height it reached just with a stopwatch, just with time. Because gravity, we know so much about what happens when the ball goes through the air. Okay? All right. Any other questions about this? No? Okay, that's it.